Hello everyone. Today we will be starting on some numericals on uniform circular motion. So these are the basic formulae that we need, and we have the first question. All right. A particle is moving on a circular path, all right, and it covers an angle of 20 degrees, all right, in 5 seconds, and we want to calculate its angular velocity, and the radius is 8 meters. All right, so we want to calculate uh, the velocity as well, not just the angular velocity but also the velocity, like its original velocity. Right, so we know that omega is equal to theta upon t. So omega is equal to 20 upon 5, right? But no, that's wrong, because this 20 degrees is actually not in radians. So you have to convert it into radians, and this is equal to pi by 9. Alright, so pi by 9 divided by 5, so times 5 is equal to pi by 45. Alright, so this is radians per second. Alright, so this is omega, and wait, let's take this as 5 meters. Alright, so the velocity is equal to r theta, right? Oh, sorry, r omega, which is equal to 5 times pi by 45, which is equal to pi by 9. Alright, meters per second. So this is in radians per second and this is in meters per second, because this is the angular velocity, right? How much theta it covers in a certain amount of time. For example, if we have two circles over here, alright, which are concentric, alright, they have the same center, then these two, if they have the same time period, alright, so they cover the same amount of distance in the same amount of time, that means their angular velocity is same. Alright, but since the radius, alright, the radii of them are different, then they will have different velocities, but they will have the same angular velocity. So let's move on to the next question, which is a little bit tricky, but it's doable. Alright, so the second one is calculate angular velocity of hour hand clock. Alright, so hour hand clock, we want to calculate the we want to calculate the angular velocity, alright, of the hour hand clock. So the hour hand clock, alright, it's like this. So it takes 12 hours, right? It takes 12 hours to make one rotation. So 12 times 60 times 60, which is equal to 12 times 3600, which is equal to 41200. Alright, so it takes 41200 seconds for one rotation. Alright, so we have the time for one rotation, it takes 41200, and the theta that it covers in this process is 2 pi radians, right? So omega is equal to theta upon t, which is equal to, now this t is also the time period, right? So we can just write capital T, and this is just for one revolution, so we can take this as 2 pi upon 41200, which is equal to pi upon 21600. Alright, oh, I'm sorry, this is 43200, so this is 21600, and this is equal to 3.14 upon 21600, and this is equal to 314 times 10 to the minus 2 upon 21600 times 10 to the power 2. 216 times 10 to the power 2, which is equal to 1.45 times 10 to the minus 4. Alright, radians per second. Alright, so this is the average angular velocity of the hour hand of a clock. Alright, so now we have another question. Alright, an object revolves uniformly. I'm so sorry. An object revolves uniformly in a circle of diameter 0.8 meters. So diameter equals to 0.8 meter, and it completes 100 revolutions in 1 minute. Alright, and we want to find its time period and its angular velocity. Alright, so it doesn't want us to find the velocity, so we can just scratch this because this is useless. And it's saying that it completes 100 revolutions in 1 minute or 60 seconds. So it completes one revolution in how many seconds? So that means 60 upon 100, which is equal to 3 by 5. Alright, so in 0.6 seconds it completes one revolution. Alright, and omega is equal to 2 pi upon t, right, which is equal to 2 pi upon 0.6. This is 0.3. This is equal to 31.4 upon 3, which is equal to I'm so sorry. What? 0. So it takes around 10.46. Right. It takes around 10.46 radians per second in order to make one revolution for this circle right here. Alright, with diameter 0.8 meter. So yeah, so this is pretty much it. I'll be discussing some more advanced numericals based on kinematics in the next video. Thank you.